So we'll talk about the amortized analysis for algorithms. I'm gonna, just give like a brief definition of what it is and some examples to get the idea across. And then we'll also talk about the potential method, which is bookkeeping method for keeping track of amortized costs. So first, let's define what amortized cost is. Suppose we wanted to open up a Dunkin' Donuts. And let's say, for example, I don't know what the cost of opening. Oh, okay. I don't know what the cost of opening a Dunkin' Donuts is. Anyone happen to know? I think it's something like $800,000. But anyway, let's make the math easy. Let's say it's $1 million to open up a Dunkin' Donuts, and then maybe $1 per donut, for dough and paying employees to make the donuts and sell the donuts or whatever. So let's say it costs us $1 to make the donuts. So $1 to make each donut. So we would pay $1 million up front, and then we would pay $1 per donut to make the donuts. So the question is, how much does it cost to make a Dunkin' Donut? And the answer is the first donut costs $1,001 to make, and then the rest of them cost $1 each. So what we might want to do in our pricing for the donuts is, if let's say we want to make a $1 profit per donut, we would sell the first donut for $1,002, and then all donuts after that we would sell for $2. So what's the problem we would run into? Well, the problem is we would have trouble selling the first donut, because nobody's going to pay $1,002 for a donut. Most people probably won't even pay $2 for a donut. But anyway, that would be a problem. But based on our cost analysis, the first donut did cost $1,001 to make. So we have to just rethink about what to do with this $1 million cost, which only happened one time. And what we might want to do is scatter that cost over some number of donuts. So using the same example, suppose we decided we're now just, what the analysis we're talking about now is not going to make our algorithms run faster. It's just a way of thinking about the cost of them, and maybe in our thinking we can convince ourselves that it's cheaper than meets the eye. So what we're going to do is we're going to make an assumption, like let's say we're going to make 1 million donuts over the course of owning this franchise, and we can take that $1 million initial fee to buy the franchise and scatter that across the 1 million donuts. So now, that being the case, then it only costs $2 per donut, but this is under the assumption we make 1 million donuts. If we make 1,000 and then stop, our analysis isn't quite right. So assuming we make 1 million donuts, we can then convince ourselves that each donut of the million, let's say we're going to make 1 million and then we're going to close the business down, each donut of the million costs $2 each. The 1 million gets scattered across all the donuts, and then the $1 per donut gets also added to the cost of the donuts. Okay. And then if we want to make a $1 profit per donut, we'd have to then sell them for $3. Now this accounting method works only if we make 1 million donuts. If we don't make 1 million, then there's something off in our accounting. Okay. So this is a definition off of, not Wikipedia, but maybe Investopedia, the investment encyclopedia, of what amortization is. So basically you're taking a big amount of money and you're scattering it over time. Or some cost, and somehow scattering, cutting it up into maybe even buckets, or buckets that just make it easier to retire the debt. Okay, so let's go over an example, a more computer science-y type of an example, where we're going to have a binary counter. So we're going to have a number like 0000, and then we add 1 to it, and we get 0001, and we add 1 to that, we get 0010, and so on. And we want to calculate how much work is going to be done in incrementing the counter. So every time a bit gets flipped, that's considered a unit of work. So it's, it's kind of like Vanna White is coming out and flipping the bit over. So we're going to go from 0, 0, 0, 0 to 0, 0, 0, 1 requires 1 unit of work. We flip this 0 to a 1. Okay, then to go from 0, 0, 0, 1 to 0, 0, 1, 0 requires 2 units of work. This 1 had to be flipped to a 0, and then this 0 had to be flipped to a 1. So there's 2 units of work to go from 1 to 2. Then to go from 2 to 3, we just needed to flip this 0 to a 1. Everything else stayed the same, so there was 1 unit of work. To go from 3 to 4, we had to flip, this 0 had to become a 1, this 1 had to become a 0, this 1 had to become a 0. So there were 3 units of work to go from a 3 to a 4. And then you could just follow the pattern. So it starts to look like, let's say we wanted to ask ourselves, how much work is involved in running a binary counter? Something that just goes from one number to the next number to the next number and so on. So if we went through n numbers, if we counted from 0 up to n, how much work would have to be done? Well, there's n numbers, and then on each of those numbers, how much work is done? Well, sometimes it's 1, sometimes it's 2, sometimes it's 3, sometimes it's 4. Depends on the numbers. So for example, a 4, when we went from 0, 1, 1, 1, from 7 to 8, we had to make this 0 a 1, the 1 a 0, 1 a 0, 1 a 0. We had to change everything. So sometimes it's 1, sometimes it's 2, sometimes it's 3, sometimes it's 4. It's kind of it looks kind of like maybe some random number for all these bits. So if we said that there were k bits, in this example it's easy to follow, k equals 4. It looks like there's n numbers and then k bits where we use some or all of the k bits. So it starts to look like it might be order nk. The amount of work to count up to number n from 0 to n minus 1 would take n times something, it looks like about half of k. Some random amount of the k numbers are being flipped around. So it starts to look like it's on the order of n and then maybe half of k, which is on the order of nk. So that looks like, a pretty big number. What we're going to try to do is, use a trick like with the Dunkin' Donuts. We're going to take the $1 million and kind of scatter it to see if we can kind of push some of the work around, some of the work that's being done, charge some of the bigger fees, like this 4, against other donuts. I'm going to try to do something like that. So, so let's take a closer look at what's going on during the operations of this algorithm. The algorithm says take a series of bits and add 1 to it. So, notice that when we increment an even number is a number where the lower order bit is 0, right? 0, 2, 4, 6, 8. When we increment an even number, we just turn the 0, the lower order 0, to a 1, and we're done. So if you notice, every other number, 1, 1, 1, every other one requires 1 unit of work. We're converting an even number into an odd number, and that only requires 1 bit being flipped, and then we're done. The odd numbers are the ones that are kind of a problem. So what ends up happening there is that what happens there is when we add 1 to an odd number, let's say for example 3, what do? Well, we could think of it like this. We're starting from the left and we're saying if you see a 1, flip it to a 0. And keep doing that as long as you see ones. As long as you see ones, make them zeros. And then the very first time you see a 0, make it a 1, and then we're done. And if you think about it, you could combine these two ideas together, because what we're really doing is we're going through all of the numbers and we're saying if the number is, so we're going from low order bits to high order bits, and we're looking for our first 0. If we hit a 0, we turn it to a 1 and we're done. If we hit a 1, we turn it to a 0 and we keep going until we hit a 0, and then we turn it to 1 and then we're done. So for example, when we change a 7 into an 8, we coming in here, we see a 1, we change that to a 0. The next one, change that to a 0. Next one, change that to a 0. And then we see our first 0, we change it to a 1 and we're done. So this one is the most expensive out of the first 0 through 8 numbers. Okay. So does this make it seem, can you think of any accounting trick that makes it seem like, hey, maybe this ain't so bad. Maybe this is not an order NK operation, but maybe it's something less. Well, first of all, we're seeing half the time it's 1. So that's kind of good news. So it's not really random numbers between 1 and 4, just randomly picked numbers. There seems to be a heavy emphasis on 1 coming in. 1 comes up 50% of the time, so that's kind of good news. Makes it look like it's less work than meets the eye. Is there anything else that we could think about? That somehow we could amortize, maybe take the cost of some of these operations and scatter them onto other operations. Can we take some of our cost of some of our donuts and move them over to somewhere else? Is there something we could do like that to make it appear to us like it doesn't cost so much per operation? Okay, so this is probably something you guys have done at some point. Going to school here on the Jersey Shore. At some point you've taken New Jersey Transit up to New York City. And you can go two ways. You can get on the train here in Long Branch and pay, right now it's $10 one way, and it's $20 round trip. You figure you might get a discount if you buy a round trip, but you don't. You get discounts when you buy like weekly trips or monthly trips, but round trips you don't get a discount on New Jersey Transit. Okay, so what we can do then is we could go, there's two ways we could travel up to New York and come home. One method is where you pay $10 to buy a one-way ticket and you go up to New York. Then when you're ready to come home, you buy another ticket for $10 while you're up in New York, and then you come home. So that'll cost you $20 for a round trip. The other way you could do it is you can buy a round trip ticket while you're here in Long Branch, and you get two tickets actually. You pay $20 and you get two tickets. One ticket that gets you up, and then another ticket that gets you home. If you buy the round trip, it's kind of like you're paying $20 to go up, and it's free to come home. You could think of it that way, instead of 10 each way. You had to lay out $20 on the way up, and coming home you don't have to take out any money out of your wallet or purse. Okay. So two ways to do it. One is you prepay for your ride home, and one you don't. Ends up costing you exactly the same either way. But it's two ways to do the same thing. It's just basically two different ways of looking at doing the same thing. Okay, so let's go back to this example. So isn't it true that every bit, they start off at zeros, they go to a 1, and then at some point they go back to 0. It's kind of like a round trip, right? So what we're gonna do is, instead of, every time a 0 becomes a 1, we know, if this counter runs for a long time, we know if it becomes a 1, it's gonna become a 0 again. So we might as well buy a round trip, right? We might as well say, look, every time a 0 becomes a 1, instead of paying the cost of a one-way ticket, let's buy a round trip. We'll pay a cost of 2. Every time a 0 becomes a 1, we'll pay a cost of 2. But the good news is when it goes from a 1 back to a 0, it's a free ride, because we bought a round trip. So, this is just the same exact example with a different accounting system that maybe clears things up for us. So, to go from 0, 0, 0, 0 to 0, 0, 0, 1, you can kind of think of this as like we have 4 employees working for us and we're sending some of them up to New York and back. The cost to go up, so let's consider a 0 to a 1 is like a trip up, but we're going to buy round trip tickets now. We're going to pay a cost of 2, and we send a guy up to New York. And now what do we have? We have 3 people here in town and 1 up in New York with a free ride home. So we paid 2 to go from 0 to 1. Instead of in the last example, we paid 1 and then the guy had to buy a ticket up in New York to get home. So now what we're doing is we're saying to go from a 1 to a 2, what do we do? What has to happen? Well, one guy comes home, but he's coming home for free because he bought a round trip ticket. Another guy is going up, and we're always buying round trip tickets with this new method. So to go from 1 to 2, that was a cost of 2. Now to go from 2 to 3, we have a guy up in New York and we have a guy down here in Jersey. We send him up to New York, but we buy a round trip ticket. So that costs 2. So to go from 2 to 3, that costs 2. Okay, now, if you follow this one, you kind of get the whole pattern. We have 2 people up in New York and 2 people here in Jersey. To go from 3 to 4, 2 people come home, but they come home for free because they bought round trip tickets. And we paid earlier. Then we send a new guy up. We buy him a round trip ticket. So we're always buying round trip tickets. And the number of zeros that get incremented to 1, we said earlier, a couple of slides earlier, there was always exactly 1 time. So we always bring, every time we increment a number, we bring some number of people home, and then we send one guy up with a round trip ticket. We always send one guy up with a round trip ticket, and then maybe not, some people come home. So we could think of it as though every increment takes 2 units. It's not quite what's happening, but it's just a different way of thinking how we're paying for it. When we were buying one-way tickets, we got all confused and couldn't keep track, and it looked like it was order N times K. It looked like it was costing something like $20 each way. So now, $20, I'm getting my examples confused. So now, with this new accounting system, it's just a different way to look at it. We're not changing how much it costs, we're just looking at it differently. With this new way of looking at it, every operation costs exactly 2. That's not really true. The first one cost 1, the second one cost 2, the third one cost 1, the fourth one cost 3. But this 3 became a 2 because 2 people rode home for free and only 1 went up. 2 people who paid earlier. And it would actually be paid, it was these 2, this one and this one. So this 2 was one of these guys overpaying, and this 2 was this guy paying double. And now both of these people came home for free and one guy went up. And he's prepaying for the next time he goes back to 0, which would be here. Okay. So, you guys are quiet, meaning this all makes sense or this all makes no sense, right? Okay. So I'd like to somehow capture this idea using a potential function. So the potential function is, it looks a little confusing, but the potential function is basically something that's gathering up value that's not necessarily paid on the current operation, the donut you're currently making, but maybe it's some costs that we're gathering up into some function that we're going to somehow spread out over all our donuts or operations, whatever you want to think of them as. So what we're going to do is we're going to say, let me just go quickly through the definition, and I think maybe on an example it makes a little bit more sense. We have a potential function phi, which maps data structures. I think that's phi. Forget, I'm not good at Greek letters. So we have a potential function, this thing, that maps each data structure, di, to some real number. So it's just a function, you give it a data structure and it spits out a number. And it's the potential associated with that data structure. We want the potential of the 0, 1, the initial data structure to be 0, and then all the other ones could be 0 or some positive value. Okay, so the amortized cost of each unit of work is equal to the actual cost. So kind of think of it just as I'm going through this function. Think of the donut example. The amortized cost, which ended up being $2 per donut, is equal to the cost to actually make the donut, which was $1, plus out of that $1 million, we're going to grab a piece of that amount and add it onto this donut. So the amortized cost is the actual cost plus this overall, monthly charge or whatever, some charge that's going to get a piece of it added to the donut or the unit of work that's being done. Okay, so if we just clean this thing up, we have the sum of all the amortized costs is equal to the sum of the actual costs plus the cost of the di to the di minus 1. How much the increment is. Again, this will make sense in a second. And then taking away this parentheses and then realizing this term here in this series is doing what they call telescoping. di minus 1 plus di minus 1 minus di minus 2 plus di minus 2 minus di minus 3. The first term and the last term survive. The n and the 0 survive. Maybe that should be n minus 1. So the highest term and the lowest term are the ones that stick around. And then the sum of all the costs of all the donuts plus the overall big bill that got amortized over the whole range. So in the donut example, this would be like the sum to make 1 million donuts. It would be the sum of the cost to make all 1 million donuts. So this would be 1 million. And then the potential would be $1 million minus $0, which would be $1 million. So it would cost $2 million to make 1 million donuts. Let's go over an example. Let's go over the binary counter example again, and we'll come up with a potential function. So the potential function is basically storing up values that need to be scattered over the course of the upcoming events. So we're going to let this function be equal to b, the number of ones in I, the number of bits that are turned on to 1 within I. So for example, the cost of changing 0, 0, 0, 0 to 0, 0, 0, 1 is going to be this. It's going to be the actual cost, which is 1, right? We're changing 1 bit, the actual cost. Then we're going to add di, so the state we're going to. There's a 1 here, there's 1 bit is a 1, and this one has a 0. So it ends up being 1 plus 1 minus 0, which is 2. So again, this is the using the round, I just want to go through this slowly. This is using the round trip technique. So we're saying if we use round trips, then all in our counter value, all the ones represent somebody who's up in New York who has a free ride coming to them. So it counts up how many free rides we have available to them. It's kind of how much money's owed to us. You can think of it like that. So the cost, the amortized cost, so basically we're coming up with a function that's going to keep producing 2's. So it's basically, it's this. We want to come up with we want to more formalize where these 2's are coming from. We chatted about the fact that they're coming from, you know, we prepaid, all our riders go, pay double, pay round trip, and then they come home for free. But we just want to more formalize that, because sometimes some other analysis of algorithm might not be as clear as just, you know, buy a round trip and it's easy to follow. It might not be that easy. So anyway, what we're saying is the cost, the actual cost, if we weren't using this trick, would be 1 bit got changed. So the cost would be 1. But now we're saying we're going to go from a potential of 1. This is somebody who has a free ride coming to them, and this is nobody has a free ride coming to them. So we have 1 plus a free ride, and the state before that we had no free rides. So what we basically did to go from 0 to 1 was we incremented and we bought a round trip ticket. So we're in a position, so the cost ended up being 2. 1 to get a rider up to New York, and another one because they bought a round trip ticket. To go from 0, 0, 1, 1 to 0, 1, 0, 0, the actual amount of work was 3 units of work. We had to take this 1 became a 0, this 1 became a 0, and this 0 became a 1. So the actual amount was 3. And then we went from having 2 round trips that were prepaid to having 1 round trip that was prepaid. So our potential dropped. We actually lost some potential. We did 3 units worth of work and we lost some potential. So now that put us at that evened us out at 2. So this number, this plus 1, and here we have a minus 1, that's this number. That is this number. We're taking the actual cost, and then this number minus this number is how much change, how much free stuff do we have coming to us, or how much free stuff did we lose in the process of doing this operation. So these 2 numbers are keeping track of some larger number that we're trying to amortize over all of our values. So, the most important part of this analysis would be the fact that we want to come up with this potential function. We would feed it in our current state. The textbook says it's our data structure, but we would feed in our current state, and based on that state, some number, 0 or a positive number, comes out. And that function should somehow keep track of some amount that we need to scatter over the remaining operations that are to come in the future. So for example, this 2, when we were at when we're at this state, 0, 1, 0, 0, it's kind of like we have 1 return trip prepaid. So there's a value of 1, meaning the method we're using by buying round trips, we have owed to us 1 round trip. Here we had 2 round trips owed to us, and we burnt them both by going to this number, but then we booked another one. So we went from being in a state where we had two return trips coming to us, prepaid coming to us, to now we only have one, so we lost some potential. Because, you know, two people came home and one went away. So we've lost some potential. And then we would go, you know, so then we go the actual amount of work, and then this 1 minus 2, that loss of 1 is how much saved up, how much banked value we have lost. So we're looking at, you know, like I said, we're looking to choose a function that maps to the behavior, which is another way of thinking of what's going on in the algorithm. So, like I say, another way of thinking of it was we buy round-trip tickets. And then this function definition takes into account the number of ones is the number of round trips we've paid for, and we've gone up to New York and we just haven't come home. So it's like how much banked value we have. And so this number minus this number is just taking that bank value and somehow intelligently scattering it over our operations to hopefully give us a better looking answer to the question. So an important thing to remember with amortized analysis, you're not making your algorithms better. You're convincing yourselves that your algorithms, which maybe are pretty good, are actually a lot better than you thought. Hopefully that's all you're doing. So it's just a way of convincing yourself that your algorithm has a better running time than what meets the eye.